Hi, good morning everyone. It's a great honor to present here at the EMI Conference 2025 in this beautiful city of Anaheim, California. I sincerely thank you, my advisor, Professor Umar Nofal, for his invaluable guidance throughout my research. I appreciate the opportunity to share my work with such a distinguished audience and look forward to meaningful discussions. And thank you for all of your attention. So we highlighted how the resolution of our flood modeling significantly influencing the results of flood risk analysis, higher resolution models capturing their finer details in topography and water flow, leading to more accurate identification of flood-prone areas. Also, our analysis demonstrate that choosing the appropriate modeling resolution is crucial for reliable flood risk assessment, which directly impacts decision making for disaster preparedness and mitigation strategies. And also by understanding this impact, we can better tailor flood mitigation plans to the specific characteristics of the area, ensuring effective resource allocation and protection for vulnerable communities. So the introduction has the study on flood risk analysis. It outlines the motivation and context for our research, emphasizing the increasing frequency and impact of flood due to climate change and urbanization. We discuss how accurate flood risk assessment is critical for planning and disaster management. Also, the introduction highlights the challenges faced in the flood modeling, such as trade-off and model between detail and computational resource. Also, it sets the stage for understanding why our focus on modeling resolution is important, as it directly affects the reliability and usefulness of flood risk prediction. We selected Lumberton, North Carolina as our case study area due to its history of severe flooding and its vulnerability to hurricane impacts. So the image shows significantly that the rainfall for Hurricane Matthew, which occurred in Lumberton in October 8, 2017, which evident the highest rainfall area from NOAA climate we have. And also the population, about like 20,000 approx has been faces flood threats that might damage impairs its infrastructure as well. So the slide summarizes the extensive impacts of Hurricane Matthew in North Carolina. As we can observe that the FEMA reports 71,000 households has been like damaged, and also around like 777 million USD has been uninsured. Also, the hardest city that had been hit by the Hurricane Matthew is among Lumberton as well. And also from the transportation impact, we can see that 635 roads were closed at peak due to the hurricane hit by Matthew. These slides illustrate the comprehensive framework we use for flood damage analysis. So the workflow that we can observe that starts with the data preparation, which where hazards map, building archetypes and cost ratios and shapefiles are loaded and processed. So this includes the extracting building characteristics and flood depth to prepare the spatial data analysis. So after that, we have the fragility analysis. We create the loss analysis as well, and then from which we get the final fragility curves, which we represent in our presentation in 3D and 2D as well. So these slides outline the methodology we followed for our flood risk and damage assessment in Lumberton, North Carolina. First, we collected the hazard data, building architect information, and flood depth maps from various reliable sources. We then applied the fragility curves to estimate the probability of different damage states for each building type based on the flood depth. And next, we combine these damage state probabilities with loss ratios to calculate the expected losses for each building groups. We use the spatial analysis to map damage distribution and generate loss estimates across the study area. And finally, the results were visualized through charts and maps to support the interpretation and decision making. as we can see, we did this in ArcGIS, that the deeper area illustrate the Hurricane Matthew, which has been hit in Lumberton, North Carolina, and there was a depth of flood has been higher in these prone zone areas, and the lighter areas show that the water depth has been lower in those areas as well. So this slide focuses on the diversity of building archetypes, essentially different types of building that were considered in our flood damage analysis, and how this group into what we call the loss group 1 and loss group 2. So we did it for loss group up to loss group 5. So the reason why we're grouping them is because to analyze every single building individual would be too complex, and individually would be too computationally expensive. So we group them, group similar building types into categories, which is called loss group, so that each building should share similar vulnerability and expected flood damage behavior. So as we can see that we have indexes the F1 archetype and F2 archetype into group 1, and group 2 has the F3 and F4, group 3 has 5 and 6 archetypes, group 4 has 7 and 8 archetypes. So we did it up to like 15 archetypes, which comprises of the first group has 10 archetypes, and the group 2 has the 7 archetypes, and 7 archetypes. In the seventh archetypes, we can see that it has the 15 archetype as well. So we did it for group 3 and group 4 as well. So as we have a question in mind, like what is the F1 and F2, F3 and F4? So F1 is one-story residential building, F2 is the one-story, F2 is the residential building on grade foundation, and F1 is the residential building with the crawl space foundation, and F3 is the two-story residential building with crawl space foundation as well. So F1 and F3 has the crawl space foundation, and the rest of the remaining buildings define the different types of usage of the archetypes that we use for our analysis as well. So now we can see that there are 15 archetypes which represent in group 5, loss group 5. Now in case of damage state, as we can observe that the damage state 1 represents the slight, and damage state 2 represent the moderate, and damage state 3 represent the extensive, and damage state 4 represent the complete. So damage state 1, 2, 3, 4 has been defined in this figure as well for easy illustration as well. So as we can see that the group 1 having archetypes 10, so we will present here the 5 archetypes. So we can observe that different damage state has been presented in this figure, and every damage state has definite changes of color patterns as well. So damage state 1 has the blue, damage state 2 is the orange, and damage state 3 is yellow, and damage state 4 is purple. So these are all for the group 5 and 10, and we can see that from the loss ratio and flood depth for archetypes of group 1 and 2, we can observe that if archetype 10 in group 1 represents the different colors for 10 different archetypes in the first group, and group 2 having the 7 archetype represent the different colors of 7 different archetypes that are showing, and the x-axis shows the loss ratio, and the y-axis shows the loss ratio, and the x-axis shows the flood depth. So we compared this like for the group 3, group 4 and group 5 as well. So from this picture we can observe that the flood depths will exceed certain levels in 4 different data sets. So for example, in group 1, in this figure we can see that the x-axis is the flood depth and the y-axis is the exceedance probability, and the cyan color represents the damage state 1, and the red one indicates the damage state 4. And we can see from the second figure on the right side, we can see that there are different methods that has been implemented, and we can see that the blue dots represent the random loss samples, while the black line shows the average loss estimates from method 1. So these are all the numbers versus damage state for group 1 and 2. We compare it like for every single buildings. So for damage state 2 has the highest one, in comparatively damage state 1 and 3 and 4. So these are done for group 3 and 4 and also for group 5 as well. So from this 3D graph, it helps us to visualize how the likelihood of each damage state varies depending on both the archetype groups. So as for example, the x-axis represents the probability, x-axis represents the different archetypes, and the y-axis represents the probability, and the z-axis identifies the flood depth of the different groups based on different damage state 1, 2, 3 and 4. And also we can see that these 3D graphs that represents the distribution of buildings by damage states across 6 different groups. So 6 different groups has been represented here, and the damage state has been represented each on the y-axis and on the x-axis, and the y-axis represents the number of buildings. So from this flood loss comparison, as we can observe that the lowest one, which has one archetype, has 79.6 million loss, and the highest one having the 15 archetypes as having the 133.11 million loss. So as we can see that the importance of details of building categorization is in improving the building accuracy of flood loss assessment. So for flood risk management and planning, using a higher number of architects provides a more realistic and reliable estimate of potential losses. So what we can conclude from this figure as well, that so what we can conclude is from the presentation as well as from the analysis that the resolution of archetype modeling dramatically shapes our flood loss estimates, so which provides the more detailed and more precise loss projections, and as also the simplistic models with fewer archetypes tends to underestimate the true risk potentially leaving communities vulnerable, and also understanding these nuances is critical for planners, engineers and policymakers who rely on accurate risk assessment to protect lives and property. So why does this matter? Actually, it matters for building a better model resolution, which means better preparedness. So it allows us to identify vulnerable building types more precisely and tailor flood mitigation efforts accordingly. So with precise damage and state probabilities and loss estimates, resources can be targeted efficiently, whether in flood defenses, insurance schemes, or emergency response planning. So as we move forward, these are the references that we use for preparing this presentation. So last and but not least, we can say that in every community, the built environment tells a story of life shaped by futures of families sheltered through storms, and of dreams built on the foundation of safety and resilience. Our research demonstrates the importance of understanding the diversity of buildings, archetypes, and their vulnerabilities, enabling us to better prepare and protect our neighborhoods from flood risk. But beyond the data and models lies a deeper truth. Behind every building is a life that matters. Children playing, elders resting, family hoping for a safe tomorrow. This is why our work is not just about engineering or statistics. It's about people's life and futures. So we move forward, let us commit to building safer, smarter, and stronger communities. Let us utilize the knowledge to advocate for resilient infrastructure that respects the unique character of each neighborhood while safeguarding its residents. Together we can turn the tide on flood risk and build a future where everyone has a safe place to call home. Thank you for being part of this journey towards resilience and hope.